All right, so I thought I would start just by giving some background on quantum radar. Quantum radar has been talked about quite a bit in some areas for a while. I just did a patent search through Google and tried to identify in any sort of patents or papers that's dealt in some way or form using quantum state entanglements to improve some sort of remote sensing function. That could be range finding, or an honest-to-gosh radar, it could be positioning, those sorts of things. And you can see there are a number of patents that have been put out there. But if you go through those patents and you try to identify, what exactly they're going to do with that entangled states, how do they plan on that entangled state surviving in noisy, lossy environments, or how do they process that information once it gets back to their receiver? It was never, a lot of those cases, it's really hard to understand exactly what they were going to do. And if you were to go inside the scientific literature and try to identify papers that deal with those concepts, at least for sensing in remote and lossy environments, I couldn't really find too many of them. However, in 2008, Seth Lloyd, he's a professor at MIT, he published a paper on quantum illumination, which is essentially quantum radar. And for the first time, he demonstrated how you could get quantum benefits for sensing in lossy and noisy environments. And before then, it wasn't really clear, but once he did that, it really, there was a lot of excitement in the radar community, and it generated a lot of interest and a lot of activity in the field of quantum radar and related topics. And so after that, there was basically a large number of papers published in this field. And so what I'm going to do is basically just try to identify some of the key challenges for quantum illumination, and then pick out some of the key concepts and papers that deal with those concepts, and discuss them a little bit, try to identify what those challenges are, how challenging they really are, and where we could go from there. So, but to start off with, probably deserves to talk a little bit about entanglement and what it is. It's not an easy concept, that's for sure. So I just have here a working definition. And it's basically if you have two separate systems that can't really be described or talked about without actually defining them together as a whole. You can't really talk about them independent of one another. You can't describe their properties or their behavior without taking into consideration the other photon as well, or the other objects. This sort of definition of entanglements is kind of just a working definition, but it should suffice for this. These sorts of entangled states, these quantum states of light, they have a number of properties that are unique and different from classical or coherent states of light. First of all, when you generate these entangled photons, they are typically generated through some sort of perhaps complicated interaction. And the regular conservation laws are enforced during that interaction. Energy is conserved, momentum is conserved. And through that conservation, you get these new particles that are created that have these ultra-strong correlations in their properties, either in polarization or in their energy or other properties like that. And these correlations are really, truly ultra-strong, stronger than any you can achieve with a classical source. So that's one thing. And what's so difficult to accept about some of these entanglement properties is these ultra-strong correlations will appear even in cases when the two photons or two electrons or whoever you're entangling, even when those are separated by very large distances. And it appears that once you actually make a measurement and the wave function collapses and you make a measurement on one of the objects, it appears that instantaneously the second photon or electron or whatever it is will take up its proper state to actually balance, make sure energy is conserved, all the other properties are conserved, and it appears to do this instantaneously, which bothers a lot of people. It basically means physics is non-local, and that's really hard to accept for many people, myself included, obviously. But so that's one of the properties that entangled states have. And another property is that when you create this new quantum state that is comprised of two or more subsystems or photons or electrons or whatever, when you write it down mathematically, you're forced to describe it using a single wave function, a single non-separable wave function. If you have two photons that are not entangled, just two photons that happen to be in the same location, you can actually write down a wave function that's separable. You basically just multiply the two wave functions together. You have to use a tensor product to ensure that you account for the increase in the Hilbert space where these photons live. But nevertheless, you have a single wave function that's comprised of two separable functions that are multiplied together. And you can make a measurement operator that acts on one photon and makes a measurement of it, and the other photon the measurement operator will act on it as an identity operator. It won't do anything to the second photon. And that's intuitive. If I make a measurement of that chair over there, it's not going to affect that chair over there, for instance. For entangled states, that's not true. For entangled states, they're non-separable, and you cannot make a measurement on one photon without having an effect on the second photon. And so that is truly also something difficult to get your mind wrapped around. And it is these ideas that people are trying to exploit to try to get an improvement and enhancement in sensing, in particular in remote environments, noisy, lossy environments. And that's what makes Seth Lloyd's contribution so significant and so really just incredible, actually, because before he came along, it wasn't really known how to actually use these entangled states to do that sort of thing, because they would always fall apart as soon as you create them in a noisy, lossy environment. They break down and become separable. They become classical very, very quickly. And so, since these states are hard to create and they're hard to get to the point where you want to make a measurements, they're difficult to actually have to live a long time in these environments. What's the benefit of using these entangled states? And so I've picked out a couple of papers that talk about methods to use these sort of entanglement properties to get a benefits. This one on the left, Entanglement Enhanced Microscope. This is in a paper that was published a few years ago, 2013. And these guys are trying to exploit the non-separable nature of this entangled state to get an improvements in resolution, optical resolution they could achieve. In this setup, they've actually used noon states, which is the kind of an entangled state, to actually image an object. And in this particular example, what they imaged was they took a small piece of glass, a glass sheet, and they etched onto it the letter Q. So very simple. And then they used their microscope setup to actually create an image of that letter Q. And they did it two different ways. They used just conventional coherent light, and then they also used the noon state, their quantum state of lights. And you can see right there, it may be hard to tell that there's a big difference, but there is a difference. The resolution they were able to achieve on the quantum state was about 23% better than what they could achieve with the conventional light. Basically, what that means is when they scan their device across that letter Q, they will see a sharp rise in the number of counts of photons that they count as they make their image when using quantum lights. And if they use conventional lights, when they just scan across the image, shown right here, as they scan across the image, they'll get an increase in the counts of photons that they have, but the increase will be gradual. It'll be kind of blurred out, and then it'll die down again on the other side. On the quantum, though, when they start counting these photons, it's very sharp and it's very distinct. And that's sort of the benefit you get by exploiting this non-separable nature of the wave function. On the other side, these guys tried to get in improvements in the classical noise limits. They're trying to beat down the noise using quantum lights and try to get an improvement in the signal-noise ratio compared to a case where they use conventional or coherent light. In this particular example, they generated a pair of entangled photons. One of those photons they directed right towards a detector, and they detected it with a photodetector. The other photon they actually directed towards the sample they're trying to image. And in this particular example, it's an absorption sort of measurements. And so as the photons travel through this sample that they're measuring, certain regions of the sample will absorb more photons, and so they'll count a small number of photons. Other regions of the sample will absorb not much photons at all, and so many photons will pass through and they'll count a larger number of photons. And the idea is, though, that in cases where there's a lot of absorption, you're going to have a lot of noise, you're going to have a weak signal that's going to be dominated by noise in the environments. And what they do is they demand that this signal counted that passed through the sample is strongly correlated with its partner that was detected with this detector. And for photons that are strongly correlated, they actually allow that to be included in their processing. Photons that have no correlation or only a weak correlation, they reject as noise. And if you look at the images that were produced, this is an image of the letter phi that they produced using a conventional source of light. And using the same amount of light, but with a quantum source, you can see that they beat down the noise by quite a bit in this particular example. And you can see a clear image of the letter phi. And so those are the two basic principles they're going to try to exploit when they're trying to come up with a conceptual design of a quantum radar. They're going to either try to exploit the non-separable nature of the waveform and increase the resolution, or they're going to try to beat down the noise by demanding that the return light from the radar is strongly correlated with its entangled partner. So those are the two basic ideas that people try to exploit. There's a number of different concepts that are described in the literature that try to use these concepts, and I've kind of listed them here. you have the one we just talked about, the interferometer. You basically use the light to try to improve your resolution. This offers, this is an active radar. It demands that you launch an entangled state of light into the noisy, lossy environments and have it come back to you. It offers superior phase resolution, so you can actually make out fine details in the target that you're looking at. One of the challenges with this method, though, is it requires that the entangled state, this non-separable state, to survive the entire transit to the target and back. And these entangled states that we'll talk about in a second are very fragile. As soon as they see any sort of noise or loss in the environments, they will break apart and become classical. And so that's one of the key challenges that limits. There's not a whole lot of activity in the radar community looking at quantum interferometric radars. They're just really hard to actually think about how to even use. I put a single photon radar here, like a single photon LiDAR. They're not really exploiting entanglements. I put it here just to be consistent because I guess in principle you can consider a single photon LiDAR as quantum in the sense that it uses a single photon at a time. They have superior range, and which is benefits, and there's no entanglement required, which is also a benefit. But they tend to be slow and short range, and they're not really exploiting entanglement, so I'm not going to really consider those. Enhanced receiver. These ideas where people are trying to improve the function of a radar or maybe even a radio by using a passive approach. They use entanglement, but they don't really demand that the entanglements propagate and survive through a noisy, lossy environment. Rather, they just transmit a classical or coherent stream of light through the environments. When it bounces off the target and comes back to them, that return signal is going to be very noisy, very weak. But they use that to actually modulate a squeezed source of light or a source of entanglement inside the receiver, isolated from the environment, so you can actually do that very easily. And by modulating the squeezed source of light, you can then generate a benefit to the signal-noise ratio. You can get an improvement in your signal-noise ratio over a classical source. It turns out these designs are somewhat complicated. They don't work at high power levels. And at the end of the day, you get a fairly modest improvement in signal-noise ratio. So people have been looking at these sorts of quantum radars. It's not really a huge effort, though. And by and large, most people have focused their attention on the quantum illumination concept that was first put out by Seth Lloyd. That is an active approach. It does exploit entanglements. They basically solve something called a quantum hypothesis test. They basically use entangled light to solve a hypothesis test. This actually gives you, as you're seeing in a moment, very super sensitivity. You can actually observe very small objects in very noisy environments. So basically, you can look for stealth targets, like a stealth airplane or a stealth bomber. What's more, and what's so radical about this idea is that it doesn't require that the entanglement survive that noisy environments. Even though the noisy environment will kill that entanglements, Seth Lloyd's approach was robust enough that you didn't really need that entanglement to survive in the first place. And the challenges here, though, that does require, in my opinion, some significant advancements in a wide variety of concepts, not just one or two, but a wide variety of concepts, and they're all very challenging quantum problems. So if this quantum illumination concept is going to be pursued further, you're going to have to address and overcome a number of fairly difficult challenges. Okay, so in 2008, this is when Seth Lloyd publishes a paper, Quantum Illumination. And if you read the first couple of paragraphs in that paper, he kind of outlines his general intuition about how this quantum radar would work. Conventional radars shine light in the direction of an object, and then they look for that weak reflection. And typically that reflection from the target, if it's in the environment, is very, very weak. The target's going to be a fair distance away. And in noisy environments, detecting that weak signal in a very noisy background can be very, very difficult. And so his intuition was that if you can entangle that signal that you're transmitting out into the environment with an ancilla, then it's going to be much harder for the background noise to masquerade around as one of your signal photons. You'll be able to tag your photon as being very special, and we can compare that with the ancilla that you generated and identify them being the partners of their entangled light that you generated. You can reject a lot of the noise. And it turns out the way he devised this, this survives even in the case when the initial entanglement is destroyed by the environments. So this was truly the first feasible approach to a quantum radar. And as I said before, it generated a lot of excitement in the community. And basically what you're doing with this quantum illumination is doing something called a binary quantum hypothesis test. Radar, and it doesn't matter if it's quantum or conventional, is basically a device that lets you do this sort of hypothesis test. And the hypothesis is the same for both kinds of radar, classical and quantum. The hypothesis is that there's a target presence in the environment someplace. And the null hypothesis being that there's no target in the environments, that the signal you collect with your device is consistent with like a thermal background. Okay, so in order to test your hypothesis, you need to collect evidence, okay? And both radars are going to use photons to collect evidence of their environments. The conventional radar is going to use coherent states of light, and the quantum radar is going to use entangled states of light to collect their information. And the basic idea is to generate a pair of entangled photons. One of these photons you're just going to store in a quantum memory device. It's never going to leave the radar. That photon is going to stay at the radar. Its partner, though, that has a strong, ultra-strong correlation, is going to be directed out towards where you believe a target may be. And then when it bounces off the target, it comes back. You're going to then take that photon with its partner, and if you detect that they're entangled, you're going to then count that photon as a signal photon and apply it towards your detection algorithm. If it's an environmental photon and there is no strong correlation, then you're going to reject it as noise. So that's the basic idea. Now, it turns out, in order to arrive at a confident decision, both radars, quantum and conventional, are going to have to use a very large number of photons to do this test and declare a target present in the environments with a decent level of confidence. In a low loss, in a low noise scenario, you can argue that a single photon would suffice. If there is no loss and you transmit a photon out to that target, if there's a target there and there's no loss, that photon's guaranteed to come back to you. So in that scenario, one photon would suffice, honestly. However, if you allow for a loss and noise, now just because that photon may or may not come back to you, you can't be sure that it's actually the photon you sent out, even by checking the correlation with the oscilla. And so you're going to demand that you actually have more than one photon. You're going to have to transmit many, many photons and then look for these strong correlations on all those photons and do that until you count enough photons where you're actually very confident that the distribution of photons that you're sampling is from the case where there's a target plus thermal environments relative to just the case where there's only a thermal environment. So those are the two scenarios you're looking at, and both radars are going to have to do this. The idea, though, is that for entangled states, the information capacity is much, much higher than you have classically. And so per photon, you can collect more information about the environments using entangled states of light than you can with coherent states. Or if you demand that both photons transmit the same amount of energy, the quantum radar will collect more information using less photons, and essentially will be very, very sensitive. You can actually look at very small targets in a noisy background. So that's what's generated a lot of the excitements, and people were very interested in that. So if you want to use these quantum states that have higher information capacity, so what kind of states are those? What do they look like, and how do you create them, and how much more information are we talking about? There was a paper that was published a few years ago where they actually examined this concept. They looked at how to actually do this parameter estimation. They're essentially estimating the reflectivity of a target in a thermal background environments. They examined how can you actually estimate those parameters using entangled states of light, specifically for the quantum illumination problem. They treated a near-term suboptimal receiver design that allows you to do that using only local measurements. And in their paper, it's actually a fairly interesting paper. I would recommend anyone read this who's interested in this topic. They provide analytical expressions that describe the information capacity or the quantum Fisher information of a variety of different quantum states. And they compare that to coherent states or the classical states that a conventional radar would transmit. And they plotted that, and this is a reproduction of their plot for a number of different cases. Here we plot the Fisher information of an entangled state relative to a coherent state. And they plot that as a function of the number of photons that you transmit out in that particular state. But regardless, for all these different states that they looked at, entangled Gaussian states or even entangled cat states, the information content of these photons is higher than the coherent photon has. And so you can see already the benefits you get with these quantum radars is they use photons that have a higher information content, and so you expect them to do better. However, you can look at that ratio. It's not a big ratio. It's less than 2 in all those cases, actually, right? So yes, these entangled states of light have a higher information capacity. They're basically more distinctive than the background photons. So you can actually pick them out easier. You have to actually do a comparison at the side of the radar, but nevertheless, they're more distinctive than the background photons, but they are not that much more distinctive. It's only a factor of 2, and that demands that you actually, when you transmit the state of lights, this quantum state that you're transmitting, it typically has to be very weak. The intensity has to be very, very low to actually get a decent enhancement over a coherent source. And this essentially kind of goes back to one of Niels Bohr's rule of thumb, where he basically says, the macroscopic is classical. As you get a quantum source and you increase the intensity, you generate more and more of those entangled states, eventually you'll generate enough of those that essentially that state will appear to start to look classical. And so that's one of the problems, and that's what's showing up here. That's just the rule of thumb, though, and it's not guaranteed. And so it is possible to find quantum states, like orbital angular momentum, for instance, that actually can have much higher information capacity than a coherent states, even with larger numbers. And so this is not indicative of the whole field, but nevertheless, you can't just run out the store and buy the run-of-the-mill entangled source of light and expect to get your radar to work well. You're going to have to find an entangled source of light that you can make bright and has a significant increase in the capacity of information that it has compared to a coherent state. And that's not easy. That's one of the big challenges already. But if you can do that, the probability of error for your radar, the probability of error either of declaring detection when the object's not there, or the error when you say there's no object, but the object really is there. Both those kinds of errors are different, but they will both scale exponentially with the number of photons you use and the information capacity of each of those photons. And it's exponential, so it really benefits you to improve the information capacity of the photon you're going to use. So we talk about quantum radars and generating these entangled states of lights and using that to improve your performance. But it really depends on the background that you're fighting against. If there is no background, then your radar is not going to have a hard time determining the presence of a target or not. So you can ask, so where do you expect these quantum radars to be built? Where would you actually, what frequency range would you want to build these radars? There's no windows here, so if the lights were to cut off in this room would literally be pitch black. There'd be no light at all, because at this thermal temperature, 300 Kelvin, there's not enough thermal energy to generate an optical photon. So on optical frequencies, there's no background, basically. If our eyes were sensitive to microwaves, though, and the lights were turned off, it wouldn't really matter. You wouldn't tell the difference. These chairs, the carpet, the floor, the chairs, everything would be glowing bright red with microwaves. They'd be emitting tons of microwaves in the background. The very air would be glowing bright red with microwaves because they would be thermally generated from the environments. And that will be the environment that the radar has to contend with. It's going to be sending out this entangled light into this really strong thermal background. And when it comes back, it has to test that light against that thermal background. And those are the scenarios where a quantum radar will work well, in strong thermal backgrounds where it's really hard to tell your weak signal from the background. If there is no background, then conventional quantum radar will have identical performances. So really, you expect a quantum radar to really work in this sort of frequency range. What I'm plotting here is the amount of thermal background attenuation as a function of the frequency of the photon. So these are microwave frequencies, about 1 to 10 gigahertz. These up to about 300 gigahertz, that's technically microwaves, so that's pretty high microwave. And beyond that, you start getting into terahertz and IR up to about visible. And this is the attenuation in red, and then this is the background. I just plotted the expectation or occupancy number of a photon as a function of temperature. And you can see that the background jumps dramatically, these microwave frequencies, and there's no attenuation really. So if you're going to build a quantum radar, it's going to really have to be between 1 and 10 gigahertz or something like that. All right, so if we want to model performance and try to understand what some of the challenges are for quantum radar, these are some of the key states that you're going to have to consider. These entangled photon states, they diffract and propagate just like coherent states. There's nothing special about how they propagate in environments. And so you're going to have to contend with the same kind of diffraction losses that a conventional radar does. And it turns out those losses are substantial. In fact, they're astronomical. So I'll show that in a second, but that's one challenge. You also have to generate entangled photons to use for your quantum radar, of course. And it really behooves you to actually generate as much entanglement as possible, because the signal-noise ratio of your radar will improve by a factor of 2 to the m, where m is the number of bits of entanglement that you can generate. So the higher amount of entanglement you generate, you're going to get a substantial bump in your SNR. You also have to worry about the target model. Some of the early papers published in quantum radar basically treated the target as a balloon or like a flat plate, just a very simple target. And in those cases, that the phase return is constant. There's no change in the phase of the photon. In real life, or in more realistic scenarios, you're going to be tracking a target that has a very complicated shape. You're going to have pieces of metals that were joined together. You're going to have pieces of metal that are welded together. You're going to have rivets. You're going to have angles, a very complicated shape of the metal object. And when you bounce an electromagnetic wave off a target like that, the phase that you get on the return essentially appears to be random compared to the phase of the photon that you sent in originally. And so the target model that you can consider is actually very important when you consider how well these radars are going to work. And finally, the receiver that you decide to use for your quantum radar. These receivers are very complicated, it turns out. Classically, we know how to build a receiver to do quantum or to do classical radar. But to do a quantum radar, the measurement process is far, far different, and it's not at all clear you can actually build a receiver to do a quantum radar in the optimal setting. And most of the papers consider suboptimal receivers that only yield a portion of the benefit you can get potentially with these approaches. So that's another challenge that has to be addressed. So here I've, from a paper that was published, I guess when was this published? In 2017, they've gone ahead and plotted out the probability of error as a function of the number of photons you transmits for a number of different cases. And here we see the probability of error plotted. It's a log scale here, and it's a log scale here. So this is the probability of error. So basically a 50-50 probability of error is someplace over here. And as you increase the number of photons, you see that the probability of error starts to drop. And we're plotting the number of photons again on a log scale. So already these are fairly large numbers of photons. And we're plotting this probability of error for a radar for a very simple target, a balloon or a flat plate or something like that. And we're going to have the optimal performance for optimal quantum radar. There's something called an optical parametric amplifier, which can be used as a suboptimal receiver. So I'm going to show that performance. And then in black is shown the performance of just a conventional classical radar. And you can see the probability of error for a given number of photons is much higher for a classical radar than it is for a quantum radar. Quantum radars can, with the same amount of light, have a much smaller probability of error. So that's basically what you expect, and that was what drove a lot of the excitement early on. But in 2017, there was some work done where they replaced those simple target models with more realistic target models, where the target exhibits this sort of phenomena where the phase of the return photon is basically being randomized. It's no longer consistent with the phase that you transmitted because the target has this complicated shape and behavior. In that case, it turns out that the suboptimal receiver, OPA, it does far, far worse even than a classical radar. So I didn't even plot it. But you can see now that rather than dropping off exponentially, so these probability of errors drop off exponentially with numbers of photons transmitted. Now the phase has been the phase information has been completely lost in this particular problem. And now you're being forced to transmit many, many more photons to get a confident decision. And the quantum optimal receiver, it still does better than a classical, but the performance gain you get is not as good, actually. And so that's one issue, how to actually get these quantum radars to work optimally in cases where the target behaves like a real target is known to. If you look at a conventional radar display and look at a target's being tracked and just look at the amplitude, you'll see the amplitude bouncing up and down by large amounts. And it turns out that orders of magnitude changes in the reflectivity measured from pulse to pulse. And that's a typical expectation for most targets. And a quantum radar is going to have to deal with that same sort of environment. So that's one of the issues that people are trying to get around right now, how to actually get these radars to operate optimally. But that was all theory up to now, but a few years ago, in I guess 2013, they actually did an experiment in a lab where they actually experimentally demonstrated the feasibility of doing this quantum illumination protocol in real life. And so this is an example of an experiment they were performing. They direct a laser onto a special kind of crystal that generates a pair of entangled photons. One of those photons they directed over towards a mirror, which was then immediately detected with a CCD. The other photon was then directed, which its entangled partner, towards an object, in this case a beam splitter. And it turns out a beam splitter is actually a nice quantum model of a target. The beam splitter will have a certain reflectivity. Oftentimes it's 50%, so the beam splitter is a 50-50 beam splitter. But that's not necessarily the case. You can have that reflectivity parameter be any value you want, really. And so a fraction of the light will be bounced towards the detector, and a fraction will just be lost to the environments. And so they're using a beam splitter as a stand-in for a target. And in this case, they also generate, using an optic element that they have in the lab, a source of thermal light. So on this beam splitter, they shine one of the entangled photons and a very large number of quasi-thermal photons. And then those photons are then directed towards the same CCD. And in this particular example, they actually achieved the same performance you'd expect based on theory. They actually saw quantum illumination give you that enhancement in signal-noise ratio, just like you would expect from the papers. And so that came, I guess, maybe 5 years after the initial paper from Seth Lloyd came out. So this was considered to be a big deal at the time. All right, so we've reviewed the theory a little bit, and we've also looked at some laboratory experiments demonstrating that quantum illumination or quantum radar can in principle be done. So now we're going to identify some of the challenges that you would face if you actually want to implement a quantum radar and use it in a realistic scenario that would give you realistic benefits in scenarios that are of interest. So one of the sources of challenges is a source of entanglement. We also have to look at the propagation. We also have to worry about how these entangled photons interact with the target. Does the entanglement survive interaction with a real target? Quantum memory is a big issue as well. You have to actually be able to store that memory at the side of the radar, or store that photon at the side of the radar for actually a substantial amount of time, enough time for that photon to travel all the way to the target and then come back. And then finally, we also have to look at the receiver. Building a receiver to do this sort of, these sorts of correlations measurements required for the quantum radar are not trivial, and that's a big challenge right there on its own. So the first one we could look at is the source of entanglement. So I just put down 3 different sources of entanglement that you could potentially consider for a quantum radar. The first one is what's available right now in most optics labs based on spontaneous parametric downconversion. And here's an example of just a crystal that you would use that could give rise to these correlated photons or these entangled photons. It's called a BBO crystal. Essentially, it's a nonlinear process. This medium has a nonlinear integral refraction. And so when you shine a light onto it with a certain probability, it turns out that probability is low, like 1 out of a million. But with a certain probability, when you shine a light onto that crystal, spontaneously that photon will split into 2 lower energy photons. And when it does, those 2 photons are entangled in polarization state, it turns out. And you could use those 2 photons to build yourself a quantum radar. It turns out that these sources of entangled light really only work at low power. If you shine a laser onto this crystal and generate a small amount of entangled light and you want to generate more, you would simply just turn up the power in your laser and you would generate even more and more entangled light. However, at some point that will poop out. And now if you start to increase the power of your laser even more, instead of a single photon being converted, you start seeing multi-photon production processes start to dominate inside that crystal. And rather than just 1 photon being converted, you will then start to have 2 photons will simultaneously be converted. And instead of having 2 photons pop out of your crystal, which is now obvious they're correlated, they're entangled, you have 4 photons that pop out of the crystal. And if you grab one, it's not clear, they're not labeled, so you don't know who its partner is. And so now the entanglement you measure starts to go away. And the problem gets worse and worse as you increase your power laser, the laser. So even though this is readily available, it's an optical regime, so it's probably not really good for quantum radar. And it's fundamentally limited, or it appears to be limited, in the amount of power you can generate. You could try to do this directly to microwave frequencies. There was a paper published by Long and others where they actually described how to actually build a microwave source of entangled photons using a Josephson parametric amplifier. This actually, I think, long-term could be eventually a way to generate a bright source of entangled microwaves, just what you would want for a quantum radar. This is still early on, though. I wouldn't say it's ready to use for any sort of quantum radar, but nevertheless, there is at least a feasible path forward for building these sorts of sources of entangled light at microwave frequencies. And in the past, there was a concept to actually build a hybrid device where you would try to generate entangled photons at the optical regime and then convert them into microwaves using an optical microwave hybrid like shown in here in this paper. So that was actually fairly compelling at the time. and it's fairly interesting design. It turns out they're very difficult to fabricate, and again, these are also limited to low powers, so it doesn't look like this would be a way to go forward, but this kind of gives you the ideas of some of the approaches that people are considering in the community for developing these sources. But none of these sources are bright. In fact, all these sources are very, very dim. And so you can ask, so how many photons can we create that are entangled? How many entangled photons can we create? And really, how many photons do we need to create? So what I've shown here are 2 radars. This is just from Skolnick, which is the radar handbook that's been around for ages. But if you dig into that book, you'll find examples of these 2 radars. This is a radar called the SPS-40. That's on old Navy ships, old destroyers, cruisers. And this is PAVE-PAWS. This is actually a huge building, so this is a very, very large radar. It's used for ballistic missile defense, tracking missiles that are like 1,000 kilometers away. So that's a very big radar. This is designed to look at planes that are, maybe 100 kilometers or so away. So these are both decent-sized radars. They operate at, megahertz frequencies, 0.5 gigahertz basically. That's roughly in the range where you'd want a quantum radar operate anyways. They have short pulse widths, 60 microseconds or even a millisecond, I suppose. That's important because for a radar to be useful, you need to have short pulses to get accurate estimate where the target is. And that's useful because if you want to defend yourself, you need to know where that target is. If you use longer pulses, you're going to get very poor range resolution and you won't be able to act on the information. So it's very important for a quantum radar to have pulse widths that are, roughly in line with these pulse widths, so very short pulses. The peak power of these conventional radars, is fairly large to be honest, 250 kilowatts, 600 kilowatts. Normally you don't do this, but you can actually then use this information and estimate the number of photons per pulse that's transmitted by these radars. And it's truly astounding. Even the small radar transmits 10 to the 25 photons per pulse. So that's a huge number, 10 to the 25. But the reason they generate so many photons is that they diffract. These photons, as they propagate away from the antenna, they spread out in spherical wavefronts. And you could try to estimate the number of photons that come back to your radar as a function of range using a simple formula shown down here. Essentially, you generate your power. You have a power source, you generate the light, you transmit it with an antenna. As soon as those photons leave the antenna, they start spreading out up in a spherical wave, and the power density drops off like 1 over r squared. They hit that target, and then the target, the light bounces off the target and again starts to spread out in a spherical wavefront, and you have another 1 over r to the squared reduction in the power density. And then the antenna has a certain size, it intercepts a certain amount of that light, and then you with a receiver, process that information and try to make a detection. But the key here, though, is that the energy or the number of photons drops off like 1 over r to the 4th, where r is the range of the target. And these targets are far away. They're like 100 kilometers away, and you have to express that in meters. So pretty soon you get these very large numbers raised to the power 4, and you can see what happens to the number of photons you get. At 1 kilometer, the photons you get back is a very small fraction of what you sent out, 10 to the 12. At 10 kilometers, you get even less, and of course, at 100 kilometers, you really start getting small numbers of photons. And 1,000 kilometers is a big distance, but you literally get handfuls of photons at 1,000 kilometers distance that come back to the radar after transmitting 10 to the 25 or 10 to the 28 photons. As an example, there are probably better quantum sources of entangled light that are brighter. I wasn't able to find one, but there must be out there. But this paper from 2018, this is actually a fairly bright source of entangled light. And it kind of gives you a feeling for the state of the art, what you could do right now in terms of generating entangled photons if you wanted to build a quantum radar. And this one is able to generate 100,000 pairs of entangled photons per second per milliwatt of input power on that crystal. But that's per second, and we really want to look, something on the order of a microsecond. And so 1 microsecond pulse from this source at 1 milliwatt input power, you wouldn't even get a pair per pulse. And if you go up to 1 kilowatt of power onto that crystal, which is a lot of power actually, you would get something on the order of 100,000 photons in that pulse that you could use to perform your binary quantum hypothesis test. That sounds a lot, but these radars are using 10 to the 25 photons. And so this is a very, very small number, and this will dramatically affect the range you can achieve with your quantum radar. And so not only do you need photons that are entangled and have a high information capacity that are very distinctive from the background, you need to generate a huge number of those photons in a very short period of time. So that is one of the key challenges for quantum radar. Okay, but it's not the only challenge. There are other problems that you have to tackle, and one of them is related to the propagation. So it turns out, entangled states are very fragile. If you propagate entangled states in a lab, like you generate entangled states and use it for some function in your laboratory, it's probably a very well-controlled environment. There's no loss in that lab. There's no noise in that lab. And you could do whatever you want with those photons and expect to get good performance. But a radar can't do that. A radar is destined to transmit these photons into a lossy, noisy environment, and it has to contend with that. And it turns out these entangled states are very fragile. Whenever these quantum states of light propagate through this environment, it's unavoidable to have some sort of interaction with the atmosphere or whatever the environment is. And even though this interaction may be very weak, each time this photon bumps up against an atom of some sort, there's going to be some sort of transfer of information, perhaps even energy or momentum. There's going to be some exchange with the environments. And it turns out that this exchange of information, this information transfer from the photon the entangled photon to the environments, that actually, every time you do that, every single time you have an interaction and the photon gives up some information, that photon state, that quantum state, starts to become more and more consistent with the information that was disseminated when you had an interaction. An extreme example would be a measurement. If you have a quantum state and you make a measurement, that quantum state is projected onto one of the eigenstates of your measurement operator. And so there the photon is now 100% consistent with the measurement you just made. You can imagine the environment is actually making a lot of very weak interactions. Every time you send this pulse through the atmosphere, all the photons that it went through, those photons are now, all the atoms that it traveled through in the atmosphere, all those atoms are changed by a tiny bit. And in principle, you can go out there and measure those atoms. And so a small amount of information was transferred to each of those atoms. And so as this quantum state plows through this atmosphere, it's giving up more and more information. It's becoming more and more consistent with these sorts of measurements. And it turns out that actually wrecks the coherence of this superposition state that you created when you created this entangled state. And very quickly, this entangled state will break down into a mixture of states, and the entanglement is destroyed. And in fact, there was a paper that was fairly interesting. There's an example, or here's the title of the paper here. They actually considered, how quickly will that entanglement be broken in the environment. And so they have an entangled source, they have a detector, and they transmit these entangled photons through a lossy, noisy environment. And I've just reproduced their calculations here. It's not that hard, you could do that. Here is a measure of the entanglement of the photon state. Large numbers or high levels of entanglement, up to the maximum level entanglement for this particular case is right here. And 0 means that the entanglement has been broken. There's no more entanglement. It's basically a separable state. It's basically a classical state at that time. And you can see for microwave frequencies, traveling out of the antenna, almost immediately the entanglement is broken. At 15 gigahertz, 100 gigahertz, even at 300 gigahertz, you don't go more than 300 meters. If you use red light, though, optical light, it turns out optical light can propagate through these sorts of noisy, lossy environments a lot better. They basically have a much higher amount of energy. The microwave photons are very low energy. They can interact with the atmosphere, and it doesn't take much to screw them up. So it turns out that these entangled states are very fragile, and the entanglement was broken right away. And so you could ask, so how does the quantum radar even work? This entanglement property is broken. What's happening? Well, the quantum illumination radar actually these benefits scale directly with the amount of quantum discord. Essentially, when you create this entangled states, you get these ultra-strong correlations between these photons. And when the entanglement is broken, that just means that the state is separable. It doesn't mean that the photons are destroyed or are broken or anything like that. It just means that the state can now be treated separable. And these ultra-strong correlations are not as strong as they used to be, but these correlations are still present. And it turns out these correlations can be used and exploited to improve your detection, because these correlations are quantum in nature, and they're still stronger than we can get classically, and they will decay asymptotically with time or at distance. So if you have a certain amount of correlation in your quantum states, a certain amount of quantum discord, you're guaranteed to have a certain amount of quantum discord, or these correlations will persist for asymptotically long times. It may become a very small amount of correlation, but it's guaranteed to be finite for any distance. And so it turns out the quantum radar performance scales directly with the amount of quantum discord you have in your states. And so that's why Seth Lloyd's approach works even in lossy, noisy environments. He's just looking for these strong correlations that persist even in noisy environments. Okay, so now we can also talk about what happens when one of these entangled states, or even if it's not entangled, just has a strong quantum correlation with another photon. What happens when that photon actually hits the target? There was actually a study that asked this very same question, or a very similar question. They asked, what happens to the entangled property when it's transferred between different quantum states? So for the radar problem, when you transmit this photon, it travels through the atmosphere. It comes up next to your metallic object that you're detecting. It excites a current in that metallic object. That photon is basically destroyed, and this coherent excitation of electrons then essentially generates another photon that's then essentially transmitted back to the side of the radar. And in fact, if that target is moving, that photon will be Doppler shifted relative to the first photon. So it's a very natural ask, because that photon, it's not the same photon as you sent out, it's a different photon. And it's still entangled with the photon that you have at the side of the radar? Or if it's not even entangled, is there still a strong correlation there through this interaction with the target? And so that's what these guys were essentially asking. They asked the same question. They put together an experiment that you could actually do in a lab rather than build a quantum radar. They actually directed a laser onto a crystal, generated a pair of entangled photons. One of those photons they just directed straight towards the detector, and they detected it. Its partner, though, its entangled partner, was then directed towards a target. And in this case, you can see the target here. It's actually a very thin piece of gold foil that has a whole bunch of small holes drilled into it. And these holes are actually sub-wavelength holes. They're much smaller than the wavelength of the light. And so it turns out, in this particular example, the way they did it, you end up generating, the photon approaches the metal perforated plates. It generates a coherent excitation of electrons on that plate. They're called a plasmon state, but for our purposes, it's enough just to consider them to be a coherent excitation of electrons. These electrons can actually tunnel through those tiny little holes. They don't care. They go right through those holes. They come out the other side of the plate, and then they'll radiate another photon towards the detector, and they detect it at this detector. And it turns out when they actually looked at the coincidence or the amount of entanglement between these photons, they actually saw almost perfect entanglements. So in this particular example, they demonstrated that if you can generate a pair of photons, one of those photons can actually interact with a metal plate, and that entanglement property, whatever was that information that you actually entangled, is transferred from the photon to a large collection of coherently excited electrons, which then transfer that entanglement property to another photon, different photon. And it turns out when you look at those photons, they're still entangled. So I personally thought that was fairly remarkable. I was shocked when I read that at first. But based on this limited experimental evidence, you should expect that even bouncing off photons off a plane or a balloon or something like that, the entanglement property will still survive. It's not guaranteed. You can imagine cases where the properties of the target would actually destroy that. If you could somehow disrupt that coherent excitation of the electrons in the skin of the aircraft, I can imagine you could try to then either reduce the entanglement property or maybe destroy it entirely. But nevertheless, at least at a bare bones physics approach, the entanglement survives transfer between these different quantum systems. All right, so we also need to worry about quantum memory. So it turns out when you transmit your entangled photon out in the environment, and when it comes back to you, you need to compare that photon with the photon you stored in the quantum memory. And you're going to look for a presence of an ultra-strong correlation. If that photon in your quantum memory is no longer there, if that memory device failed or the quantum photon died, then you can't actually get any benefits. So you need to have a quantum memory device that actually that allows those photons to live for a very long time. And the longer you can get those photons to live, then the longer range your radar will be able to achieve. One of the things you're going to have to do is, though, you're going to have that storage device to be engineered with a tunable coupling. You're going to have the coupling be essentially very, very weak, where the photons can have a very long lifetime in that quantum memory device. And whenever you want, so you need to be able to tune that memory such that it becomes very strong coupled to your system, and you can extract those photons very rapidly. So that's actually a very demanding engineering challenge, to actually have a quantum memory that lets you do both those things on demand. And I'm not aware of any device that will let you do that at present, but a few options that people have considered for quantum radar. You can use a fiber optic loop that demands that at least one of your photons is optical. It turns out that the best fiber optic you can find out there has a certain finite amount of attenuation. If you shine light through that fiber optic, a small amount of that light's going to decay over time. And it turns out that the maximum range of your radar, if you use a fiber optic loop, which is available right now, would be limited to 11 kilometers, which isn't very long, actually. And so you need to be able to do something better than just a simple fiber optic loop. You can imagine using an RF microwave cavity that will allow you to store photons for much longer times. One of the challenges there, though, is that you have to be able to develop a tunable coupler. And these can actually handle, in principle, high power levels. But one of the challenges with this particular case is, this entangled property is achieved for at least most of the sources, photon by photon. And so if you shove in a large number of photons into the cavity, you need to be able to extract those in the same order you put them in, so you can actually line them up with the photons that are coming back from the environments. If you're off even by one photon, then you won't see any correlation at all, obviously. And so it's not a trivial thing to use a cavity for storing these photons, but I can imagine people trying to do that. And the third option people have talked about is using an honest-to-gosh qubit. That actually is very enticing, because you can incorporate your quantum memory right into your quantum receiver and use a qubit to do both the memory storage as well as the receiver design as well. Of course, this is, also very hard. The qubits are very noisy, and it's hard to actually get them to store these photons for a long enough time to be usable for a quantum radar. So finally, the last challenge is a quantum receiver. This actually is one of the more challenging aspects and one of the more interesting aspects of building a quantum radar. Classically, if you're confronted with a system and you want to learn something about it, you're free to make a measurement on that classical system and learn something from that measurement. And you're probably not going to learn everything there is to know about it, so you can follow up with a second measurement or a third measurement. You can make as many measurements on that classical system as you want, and it's not going to change your system at all. And that's totally a good approach to take for classical systems. That option is not available for quantum systems, though. If you are confronted with a quantum system and you want to learn something about it, as soon as you take a measurement of that quantum system, you actually project it under one of the eigenstates of your measurement operator. And so if you want to follow up with a second measurement, that state's no longer there. You can't follow up with a second measurement and learn something more about it. So you have to be really thoughtful and have to come up with an approach to actually optimally perform these sorts of radar operations, a binary quantum hypothesis in this case, that extracts the most information from your quantum states as you possibly can. It turns out that process was studied by Hellstrom and others way back in the 70s, and they're still looking at it now. But it turns out that Hellstrom actually came up with an optimal approach to let you do this. It turns out that he wrote down a mathematical expression describing what that physical operator would look like, what the receiver would look like. But it was not intuitive how to convert that mathematical expression into a receiver that you can actually build. So no one really knows how to build a Hellstrom receiver that could be used for quantum radar. But it turns out you can actually asymptotically achieve the same performance that Hellstrom said you could using a quantum computer. You'd use a quantum computer, collect all the states from the environments, and then perform something called a quantum Schur transform. And that would allow you to actually achieve, at least in the limit of large numbers of photons, the same performance that Hellstrom promised. It turns out that's very hard to do, though. Quantum computers aren't available to do that right now, obviously. And so people have proposed something in the near term that could be done right now. And you basically use an optical parametric amplifier, which is essentially, in some sense, just a very special crystal. You would take your light you collect from the environments that hopefully is entangled, and then you take the light that you stored at the side of the radar, and you shine both those beams onto your crystal. And it turns out you can think of this as a phase-sensitive amplifier. And if your two photons that you're using really are the photons that you generated and one of them was transmitted in the environment, they're going to have a very strong correlation in phase just from the way they were generated. And it turns out that you just essentially shine both these lights on the crystal, and if they're the same quantum states, if they're entangled, or if they were entangled, they have a strong correlation, and you're more likely to amplify that compared to the case where it's just thermal background. And so you simply sit there, shine a light onto it, and you start counting photons. And you have to count enough photons to convince yourself that the distribution you're sampling from is from the target with thermal environment versus just thermal environment. So that's the basic approach. That works. It's suboptimal. You only get basically half the benefits as opposed to doing the Hellstrom approach. But this, in principle, can be achieved using technology available today. Shapiro, he's a professor, one of Seth Lloyd's colleagues at MIT. He actually studied this problem in detail. I encourage anyone who's interested in quantum receivers to read this paper in particular. But he described an approach that will let you achieve asymptotically Hellstrom's performance using some frequency generation, which is basically the inverse of how you generate spontaneous parametric downconversion photons. You shine both those photons onto your material, and you're more likely than not to generate a photon in the output if they were initially entangled. I won't go into more detail on that, but that essentially is, at least asymptotically, an optimal way to do the detection. So that's an important result right there. It turns out that's a very hard receiver to build, and no one's actually built one, and they don't know how to proceed to build one. And so that's a long-term project, but that could be one area that people could explore as well. Okay, so this is my last slide. So this is the expected performance of a quantum radar in these particular cases. There's the thermal background. We're going to use a modest size antenna, something roughly the size of that table, about 1 square meter. We're going to look at a target someplace in the environment that's roughly the same size, 1 square meter. We're going to use 1 millisecond pulses at microwave frequencies. And then I'm going to require that both radars achieve a decent signal-noise ratio, about 12 dB. So that's basically you're very confident that there's a target there. And I'm going to assume that the quantum radar is able to perform optimally, uses a source of entangled light, and I'm going to assume that you can turn the power up to this source arbitrarily high levels without having to worry about the entanglement property disappearing. So in these sorts of cases, this is the sort of amount of power you would have to transmit as a function of the range where the target is actually at. And in black is the amount of power you need to plot for a classical radar, and in green is the performance you would get from a quantum radar. And you can see for a given range, the quantum radar has to transmit a much smaller amount of, well, not a much smaller, but a small amount of power to achieve the same performance as a classical radar. It's just that in order to get ranges that actually mean, anything that you can actually act on, you need to have your quantum radar transmits, a huge amount of power, even to achieve, 60-kilometer range. And right now, that's like 9 orders of magnitude more power than what's available right now from standard sources. So that illustrates one of the very big challenges for a quantum radar is that it's really hard to generate enough photons to actually make a difference. So that's the end of the talk. So I'm happy to take any questions if you have any.